we are presenting our work on bringing reinforcement learning to web navigation. So to bring web navigation refers to clicking, typing, and interacting with websites to complete specific tasks. Uh, traditionally, traditionally browser automation relies heavily on rule-based system tasks like web scraping and web testing, but those approach doesn't work well, especially with high dynamics in today's website. So that's where reinforcement learning offer a better alternative. So instead of hard coding, we can train an AI agent, RL agent, to interact with website in more adaptive and human-like way. So our goal is to develop RL that can generalize across different layout in website. So application of browser automation. So there are this application following applications for browser automation: web testing, web scraping, security testing, and dynamic interactions. So, bringing RL into browser automation brings various challenges. So one major challenges is complexity of real-world system. We will come across non-RL issue like integrating it with browser or handling dynamic data. So building full RL automation pipeline can take months of time. That's why we need benchmarks. So the benchmark focus on the RL helps us to focus on RL side of the problem by removing this infrastructure complication. So and benchmark should be such that it is simple enough to run and also challenging enough so that it can perform learning in RL framework. So to address these challenges, we have this benchmark dataset, MiniVob++. It is developed by OpenAI and modified by Stanford researcher. So it contains 100 different tasks like clicking, typing, selecting, and more. Minimob++ help us to implement and compare different RL method in website environment. So here is a glimpse of what Minivob++ task look like. So each task is browser based, designed to a very specific interaction skill. For example, here we have task to click the close box and click the cross and close the dialog box. So it has a time limit of 10 seconds. So reward starts from +1 and decreases to 0 with time. So if the agent fails to click on the cross within 10 seconds, episode ends and it get a reward of -1.
So now that we understand what MiniWeb++ is, let us frame the web navigation problem formally using the MDP structure. So the state space in MiniWeb is quite rich. It can include a screenshot of the page, which is a 210 cross 160 RGB image. Optionally, as it can include a textual task description, for example, click the button 1, as well as a list of elements on the page. We might only use one or a combination of these depending on how we design the agent. For example, in the simple clicking approach, which we will see next, we'll mainly use screenshots. The action space is also quite expressive. The agent can press any combination of keys on a full keyboard, as well as move the mouse to any arbitrary XY coordinates. It can perform actions like left click, right click, double click, or even scroll the mouse wheel. The reward signal depends on the specific task. For example, for simple tasks like click the button 1, reward is 1 if the agent clicks the correct button. The reward is also time sensitive in the sense a delay can reduce the reward to something less than 1. As always, the agent learns a policy that is a mapping from states to action by interacting with the environment. Ultimately, the goal is to learn a policy that maximizes the expected cumulative rewards over time. In web navigation, this translates to learning how to complete browser tasks efficiently, like clicking buttons, selecting elements, and typing inputs, just like a human would. Moving on, So to start solving tasks using RL, we need to simplify the action space. Otherwise, learning can become very difficult. The active area of a browser is 210 cross 160 pixels. As a top 50 pixels are not used, they are used for displaying the instructions. Our effective area is 160 cross 160. So to make the action space manageable, we discretize this area with a bin size of 10 pixels. This gives us a grid of 16 columns and 16 rows, or 256 discrete actions. Each action is represented as an integer between 0 and 255. This grid representation greatly simplifies the problem for our RL agent. Instead of learning a continuous mapping for every possible pixel coordinate, the agent only needs to choose from 256 options. We will use the E3C method to train the agent, which should decide from the observation which grid cell to click on. Besides the policy, which is the probability distribution over these 256 grid cells, our agent estimates the value of the state, which will in turn be used as a baseline in policy gradient estimation. So the task for our agent is to close a pop-up by clicking the button X in the click dialog V1 environment. We will use the E3C method to train the agent, which should decide from the observation which cell to click on. The observation is the RGB screenshot of the browser image. The agent's action space is the 256 discrete click positions obtained from the 16x16 grid. The agent processes the screenshot using a convolution neural network, which then splits it into two parts. The policy head outputs a softmax probability over the 256 possible click locations, and the value head estimates the state's value, which is used as a baseline in our policy gradient estimate. Moving on, let us revise the actor critic idea. The actor tells us what action to take. It learns the policy. And the critic estimates the value of the current state, basically how good the situation is. So we define the advantage function here, which tells us how much better a particular action is than as compared to the average action. Using this advantage to scale our policy gradient helps us reduce variance and makes learning more stable. This is what E2C is, that is the advantage actor creating it. Let us see the E3C one, the method which we use to train our agent. So in RL, we face one challenge of the sample correlation. If the agent generates experience from one long episode, all the data is highly correlated. So this breaks the IID assumption required for SGD and can lead to unstable training. In off-policy methods like DQN, we handle this using a replay buffer, but E2C is on policy, so we can't reuse old samples. E3C solves this by using multiple agents in parallel environments, all collecting fresh independent trajectories simultaneously. Each worker has its own environment instance and uses a shared set of model weights. Each worker uses the shared global model to generate actions and correct experiences asynchronously. So there are mainly two ways to parallelize: data parallelism and gradient parallelism. So data parallelism is where each worker sends their experience to a central learner who computes the gradients and updates the model. And in gradient parallelism, each worker computes the gradients itself, and then these gradients are sent to the central node, where the central node aggregates these gradients and updates using the sum of the gradients. The updated waves have to be broadcasted back to all the workers. Here we can see the visualization of the process in data parallelism and gradient parallelism. All the agents use a shared net, which is the set of weights, and in data parallelism, the samples are sent back to the process 0, which is like the central worker here, which then computes the SGD updates, and it updates the set of weights for all the workers. Whereas in gradient parallelism, the gradients are sent back to the central worker, central process 0, and it computes the SGD update using this sum of the gradients. Coming to training and evaluation, we trained our agent on the click dialog V1 task. The task was simple. As mentioned, the agent has to click the button X to close a dialog box that appears randomly on the window. The challenge is to find it quickly. The training took around 8 minutes, and the agent was able to reach an average reward of 0.9. The left plot shows the average reward per episode per time. As expected, we see a curve rise and eventually plateau around 0.9, indicating convergence. The right plot shows the average number of steps per episode. The episode step chart on the right shows the mean count of actions that the agent should carry out before the end of the episode. So there are some limitations in the simple clicking approach. First of all, our agent is stateless. So it only observes the current screenshot and has no memory of the past actions. This is also due to the Markov assumption in our MDP formulation. This makes it unsuitable for tasks requiring a sequence of steps. For example, as we can see in the click button sequence task, the agent first needs to click 1 and then 2, but the observation alone doesn't reveal what was clicked earlier. So this violates the Markov property of MDP. So this turns the problem into a partially observable MDP or POMDP. Generally, the solution for this is to incorporate some information about the state, some information into the state itself. Second, some tasks include important information in text, which are image only agent ignores. So as in the following example, we see in click checkboxes, labels are dynamically generated. So without parsing that text, the agent can't act correctly. So one solution is to use OCR and another is to use text descriptions. Third, the dimensionality of the action space is another bottleneck. Even though we discretized it, the number of possible clicks is large. So this leads to sparse rewards and slow exploration. Finally, we see that some of the tasks benefit usually from human demonstration and can lead to faster convergence.
All right. So I'll explain the next section of the our presentation. So as Pramitesh has explained, like there are some drawbacks in the previous approach. Like one of the drawback is like since the agent's observation space is only the pixelated image, it can't able to understand, able to solve the task effectively which contains the text description. Like as you can see in this image, like there is the task is to click tab with tab hash 3, but since the agent uh, can't able to understand the text like clearly, so it will click any of those other clickable options like tab 1 or tab 2, but because of this the agent can't able to learn efficiently since it can't able to process the textual information through pixelated image. So one solution is like we can add text descriptions into the input of the input observation space of the agent. So we will add this text description by using LSTM. So previously there was a CNN layer which extracts the features uh, which are necessary for extracting the features from the image, pixelated image. Now we can now in this updated approach we are adding another LSTM head to our neural network. So LSTM is a basic uh, architecture with which we can able to extract the features from the sequential data like text. So here we have used only the LSTM. So from this is the basic architecture. Like we will get some features from CNN and similarly some features from LSTM. Then we concatenate these features and we will send these features to the value head and policy head to perform the uh, uh, actor critic algorithm to make the agent to learn from the features. So this is a pseudocode of how it happens. So like we have like after an episode we get a batch of image and text space. So for each image and text in the batch, we'll tokenize the text using tokens. And like this is a normal approach of processing the textual data. So we will, after getting the tokens, we will map those tokens to some specific IDs which we store in a specific dictionary. So then we will send the image batch to the CNN. Similarly, the tokens to the LSTM, and we'll get the features, and we just append these two features, and we send these features to the policy head, which will return the softmax probability of every possible action. Similarly, value head returns as the state value. So based on this, we will our model gets updated. So these are some results which we obtained by doing this multi-model based training of agent. So as you can see, like the model got able to click within, like it took a long time compared to the previous task, because previous task was simple since there is only one possible action of closing the tab. But here there are multiple actions. Like even like if the agent clicks the wrong button, then we will get negative reward and the episode will complete. So since because of this task is little bit harder than the previous task, but the agent converges within around 4 hours, and the reward is around 0.2 since the task is hard. But uh, without, like rather than sending, like training the agent without text, with text it is better. And the number of steps for the agent is also is around 5 steps. So one of the limitation is, since we are adding another feature head, so there are many hyperparameters which, like the number of hyperparameters to tune are increasing. So it is little bit harder to uh, set these hyperparameters for a specific task. Thanks.
So as mentioned earlier, we have the problem of large action space dimensionality. The methods that were discussed earlier, they work well in case the action space dimensionality is small. But however, if the action space dimensionality becomes large, the training process will become very lengthy and it may fail to converge. And in the tasks that we have seen, even for seemingly simple tasks like counting the sides of a problem, the action space dimensionality is very large. The model starts off with random exploration, and slowly it finds out few actions which are better in few states, and in that way it comes to the optimal policy. But it takes a very lengthy process, and in some cases it may fail to converge as well. So the possible ways to solve this issue is, there are many ways where like for example, one-shot learning or transfer learning or incorporating human demonstrations. We are going to see the method of incorporating human demonstrations. So when we use this human demonstrations, it's kind of a hybrid approach where we are trying to make our model imitate the human actions. But this is because the human actions are considered to be the best actions, or kind of at least good actions. And at the same time, we are using reinforcement learning for the model to learn on its own through the policy gradients that we have already discussed. So human demonstrations are uh, provided as JSON files. These are basically the observations from the human episodes. Observations in the sense we can think of it as the tuples S dash R, S A R S dash, which are basically used in the in previous methods discussed, actor critic method as well. So for incorporating these human demonstrations, we can't use these observations directly as the observations obtained from the environment. Uh, this is because these are obtained from a human policy, but A3C is an on-policy method. So we can't use these observations directly within the policy gradient algorithm. So we do kind of a supervised learning approach where we take the cross entropy loss between the actions provided by our current policy and the desired actions which are taken by the human in the human demonstration, and we try to minimize this cross entropy loss. Here we are taking the cross entropy loss between the actions. So the actions are basically a discrete entities, and therefore we are taking the cross entropy loss. And this kind of training happens with a probability of demo prob. And in each such instance, we sample a batch size number of samples from the demonstration data and perform a round of training using that data. So here both demo probability and batch size are hyperparameters. Uh, this phase of supervised learning happens with demo probability at some point uh, while the reinforcement learning policy gradient algorithm is running. So we'll just have a quick look at the cross entropy method, where we basically have a large number of episodes, but we only choose elite episodes where we got higher rewards, and only observations from those episodes are used as the desired output, and a cross entropy loss is computed between the current policy and those observations. Similarly, here the human policy can be considered as the elite observations because the actions taken by the human are considered to be at least good actions. And therefore, we are trying to push the model towards taking the actions in the demonstrations. So how does this actually help? As we already mentioned, if we don't use human demonstrations, the model starts off with random exploration. And because the action space is very large, it finds it very hard to understand the problem and find out the optimal policy. But in case demonstrations are provided, it we can as we will see in the results, the training process speeds up very significantly. It is similar to how humans learn by seeing the activities of others. So our model is trying to imitate the human activities. But at the same time, we must remember that we can't use only the human demonstrations, like removing the reinforcement learning part. This is because in that case, the model kind of learns the actions only for the states that it has observed from the human demonstration, and also it will be unable to uh, uh, distinguish the actions. It takes the same action for a given state in all situations, but it may not be optimal depending on the problem. So we must learn it. We must make it learn through the rewards so that it understands what action has to be taken in what situation. And the self-improvement and the imitation can be balanced by using the demo probability hyperparameter. And also we keep this demo probability only for the early part of the training. Suppose a specified number of frames, like the demo frames. So demo frames is also a hyperparameter here, which can be adjusted to in order to balance how much self-improvement the model has to learn and how much imitation the model has to take. So here are some results for the count sites problem, where the model has to count the number of sites shown in the figure and select the correct number. So if we had not used the human demonstrations, even after 12 hours of training, the mean reward is just -0.4. But with just 25 demonstration episodes, the reward becomes 0.5 in just 8 minutes. So incorporating human demonstrations has quite a significant effect on the training. And here is a graph that demonstrates how in 8 minutes, the model easily reaches a mean reward of 0.5